Well, I caught something. I don't think it's anything major, but it does impact how I can use my voice. So I might not be projecting as much as usual. All right, so I think we are done with compiling C control structures, unless you guys have specific questions. Let me go back to that module first and just make sure that I didn't miss anything major. This is also something that I would like you guys to read as well. Okay, so you definitely want to read the whole thing. We have nesting and labels. Okay, so section 6 is not something that you absolutely have to read. It really has to do with naming conventions. How do you make sure that your label name is well structured so that it's unlikely that you will step on the same label name again and again. So if you name your labels L1, L2, L3, at some point it becomes very difficult to keep track of which one is which one. So what I'm suggesting here is really just using the name of the construct and also where in the construct as a part of the label. And then we use a suffix, which is basically a number, so that we can differentiate, is it the first conditional statement, the second conditional statement, and so on. And if you have a loop and a conditional statement in the inside, so the loop itself has loop as the main part. So we have the beginning of the loop, the end of the loop, but inside the conditional statement, the label that I use inside the conditional statement that is inside the loop actually has loop1 as a prefix. So this way, if you have another conditional statement inside another loop, you won't be using the same, they won't have any collision in terms of label names. Is that making any sense? Because if you don't use a prefix of loop1 ahead of the label name and if, then when you have another conditional statement in the loop that is after this one, then you might end up using end if one and end if two again. So this is a way so that you can structure the name of your labels so that you basically totally eliminate the possibility of accidentally using the same label name again. Yep.
How many characters can a label be?
It is a limitation of Google Sheets. I do not know. I believe it can be very long, like whole sentence kind of long, whole paragraph kind of long. I have not tried. So if you guys want to try out really, really long label names and see when it starts to break, be my guest. All right. So this section is really just talking about this. And also when you have conditional statements, then you also add that to as a suffix. So there's an _1 to indicate this is the label that is required when we break down the conjunction. So it's probably not necessary for you guys, because I don't really see us doing complicated programs that will require this many labels, because after all, we only have 256 locations in RAM, and that includes the space for your code, the space for local variables, the stack, everything else. So I don't really see that we need to worry about this. So you can, for the most part, you don't need to read this section too much. And then this part here, okay, so a longer example is looking at this particular code here. I have no idea what it is actually going to do or whether it's useful. I just know that it is syntactically correct. So the question now is, how do you convert this code here? How do you convert this code into assembly code? So that's the question. And you can see that we are less than halfway through the module. So the rest of the module is really a step-by-step procedure to first comment out everything, and then we start to do some translation. Okay, so the global variables XYZ are really just a label followed by byte, so that we allocate the byte right after the label, and then we start to translate the simple instructions like x = 5. Okay, we can just go ahead and initialize that. So you can see how it is not really that simple, because X is a label of a particular byte in RAM. So in order to change that location to a value of 5, what you really need to do is to load the address into one register and then load the constant that you want the variable to start with into another register. And then you use the ST instruction, which is dereferencing, in this case, register A, so that we are storing the value of register B to where register A is pointing to. So register A has the label X, which is the address of one particular byte in memory. So you can see how it is not really simple. Even when you want to do something like this in C and C++, it translates to at least 3 lines of code like this. And then the next stage takes care of the inner part of the conditional statement, which is z gets z plus x. Z, once again, is a global variable, so the label z is the symbolic name of the address of a particular byte in RAM. X is the same way. X is the label of the address of a particular byte in RAM that we know in C code as variable x, global variable x. So in this case, I can give you the equivalent C code on the side, after the slash slash, so that we know what it is doing. So LTI A comma x, x being the label, is really the same thing as saying A equals to the address of x in C code. Okay. So this is where the confusion can come in. Is in assembly language programming, there's no such concept as a variable. We only know addresses. Okay. So that means x as a label in assembly is the address already. It does not refer to the value of the variable, it refers to the address at that particular label definition. So that's why that's where confusion can come in. If I dereference it once, then A becomes the actual value at that location, otherwise known as the value of the variable x itself in C and C++. And then the same thing with Z. So after I get the value of x into register A and get the value of Z into register B, then I perform the addition. And then once I have the sum, I store that back into Z. So that's why even something that looks as simple as this, if x and z are in fact global variables, it does translate into this many lines of code. So are we kind of doing okay with this or not? No, yes, maybe. Okay. Yep.
Can you just briefly, why does it make such a big difference, global versus non-global?
Okay, so the question is about global versus non-global, and before we go there, let me just double check and make sure that the original code has global variable xyz. So it does. Okay. So in a C program, when you have global variables, they are statically allocated. In other words, the lifespan of a global variable, for instance, in this case, x, y, and z, they start to exist before your program starts to run, and they persist until your program is terminated and the operating system reclaims the resources. So that's the nature of global variables. In other words, it is not only the scope that is quote-unquote global, the lifespan is also global. But when you look at local variables and not counting static local variables by definition or by default is auto, which means they only exist when you get into an invocation, and they cease to exist when you're out of an invocation. So that's the main difference between a global variable versus a local variable. It is not only the scope, but also the lifespan. The lifespan is the big difference that actually matters more compared to the scope. So we'll get to local variables too. So right now we're just dealing with an easy one, which is global variable. So this is really just step by step, going through the whole process to convert C code into assembly code. So you can see right here. Let's see. The next stage is we apply De Morgan's law, so we have a bunch of derivations here. to basically break it down to things that we can more easily manage. And by the time we get to the point where we can actually translate into assembly code, that is when we actually do the assembly code. So are there any questions about this part? It's just step by step, okay? If you want to, one way to really read this section is to print it out. And not just print out the whole thing in one single PDF, put each version of the program on a different sheet of paper. Then you can actually start to see the differences, or you can highlight the differences. So you can actually see how the program evolves from one page to the next, and then you start to understand, oh, so this construct it now becomes this construct now becomes this, and so on. You can probably imagine, this kind of took me a little bit of time to code. And let's see, did I finish the whole thing? Yep, I did. Yep, I did finish the whole thing. And so you can actually type this program in to the assembler and test it. And then you can test whether it has the same result as the original C program. There's no C compiler to convert C code into TTP ASM, so you will have to test the code in C, just using code blocks or something like that. So are there any questions about all of this? So you probably want to read it, okay, and analyze how this code evolves over time. But I can tell you that it's really mechanical to lead it from one step to the next. So are there any core questions? Okay, not like okay, how do we go from here to here? But you can ask those questions too. But are there any core questions about compiling C control structure into assembly code? And that includes conditional statements, conditions, and all the other stuff. Are there any? Yep.
What are some good places to check for actual examples of code to practice? Would you just go through a beginner's C book or something?
So that's a good question. How do you practice? I would try to get some code that is no more than 7 lines or 8 lines, to test. You can find algorithms that are fairly simple, and then just go ahead and try to convert those into assembly code, and do something that you can actually run tests on. So that on one hand you can test the C code, on the other hand you can test the code in assembly, and see whether they come up with the same values or not. Okay. Not the homework, but the lab activity today is one example to find the absolute value. Did I illustrate how to find the maximum of 2 variables and then store the maximum into a 3rd variable in this class? Not this one? Okay, so I must have done it with the other class. So that's something that we can use as well. I can show you that. Okay, this is a 440 step. Okay, so to find the maximum of 2 variables, it's relatively simple. So let's say everything is in register already. Okay, so we have register A, and we basically say if register A is greater than register B, then we do something, otherwise we do something else. And if A is greater than B, then the maximum is A, and I want to store the maximum in register C. On the other hand, if register A is less than or equal to register B, then register B is the maximum of the 2. So this code finds the largest, or it finds the maximum between register A and B, and then store the maximum in register C. Is that okay? So now the question is, how do I convert this into assembly code? Okay, the original code is only what? If you don't count the curly braces, which are actually not necessary in this case, this program is only 4 lines of code. And it doesn't use any variables. Everything is in register already, which simplifies the whole thing a lot because you don't have to load the address of a variable into a register and then indirectly access it. So now the question is, how do you translate it? What do you think? What is the process to do it? Remember the flattening thing? So the first thing is to flatten this code so that you can still test it in C and C++. Okay. So the first stage is to do it like this. Okay. So you basically say I'm looking for the negation of the condition that I have to begin with, but in that case I'm going to go to the else label. Okay. So I'm going to emphasize that we're going to a label here. If we do not go to the else label, that means A is greater than B is true, right? Because we're going to the label when A is greater than B is false. So if I fall through, that means A is greater than B is true. Then we just perform the operation of C equals A. But I also have to be careful to not fall through to the else case. So I'm going to have a go to the end if label, which is defined at the very end of this entire thing. So at this point, I can now define the else label, which marks the beginning of the else statement. And in this case, the else statement is only one simple thing, so we'll just put it here. So are we doing okay so far with this conversion, which I personally call the flattening of the structured code? So do you notice that the converted code has no curly braces anymore? Because it's not necessary. Now you might say, oh, that is not necessary because in the original code the curly braces are not necessary to begin with. Well, that may be true, but on the other hand, if I have a chunk of code here, like more than one lines of code or more than one statements, you can just put all of those here. The curly braces are no longer needed because the boundary between the blocks are now indicated by go-tos and label definitions. Is that okay? And then the second thing is I intentionally did not use indentation in this case, because if indentation is only used to mark syntactic levels of hierarchy, all of these are at the same level. The only ones that are not really at the same level and indentation really should be used if I use multiple lines would be this go-to here. Because that go-to is the then portion of the conditional statement. And that's why that one, if I want to write it on a separate line, will be indented. But everything else are really syntactically at the same level. Is that okay? So the other thing that is interesting about this converted code is this is actually legitimately C code. It will compile. Which means if you suspect that you might have made a mistake in the conversion, you can test it. You can test it in code blocks. You can test it in Visual Studio. You can test it in any C++ compiler. I'm pretty sure this will compile in Visual Studio too. I mean, this is way too simple to have any impact, based on the dialect of C++. Is that okay so far? Okay. So if this is okay, then we're gonna look at this, take it to the next level. I'm not quite ready to translate this into assembly code just yet, because we have a greater than. Because in assembly code, we can only understand less than. So how do we convert it into things that we can actually do in assembly code? It's less than or equal to, right? So we can say if A is less than or equal to B, go to else label 1, and then the rest are the same. I'm just gonna copy and paste here. Okay, is that okay? Is that a legitimate change from the version of the code before? Yep.
It doesn't make a whole lot of difference, but the else label is missing a 1.
Oh, okay. Yeah. So we just get rid of this one here. Okay, so if this is okay, then the next question is, we still don't know how to check for less than or equal to. Okay, fine. Would it be okay to, if I were to change this to that? Okay, right? Now if I change it to this, then I have to kind of get rid of the OR operator. So to remove the OR operator is actually not too difficult. We just split the conditional statement into 2. So we just copy and paste it and say if A is less than B, let's go to else label. If A equals B, also go to else label. Is that making any sense? Okay, because when you have an OR operation, it means the first condition is sufficient for me to go to the label. If the first condition is false, then the second condition is also sufficient to go to the else label in this case. So are we good so far? Okay. I think we got it down. Okay. So at this point, we can start to convert it into assembly. So to convert this into assembly, let me do this. So copy and paste again, but this time I'm going to comment out all the code here, except for the label definitions because they look exactly the same in assembly language. So at this point, I'm ready to actually do it in assembly. Okay, so if A is less than B, go to else label. We can do it in 2 instructions in assembly. Which 2 instructions do you think we can use? Compare, okay, so compare AB. And what about the second one? Now, this is where I didn't tell you which one it is. Okay, I didn't tell you whether A, B are signed or not. Okay, so let's say they are unsigned. Okay, if A and B are unsigned, what conditional branch should I use here? J, if they're unsigned. If they're unsigned, which flag indicates the minuend is less than the subtrahend? Yes?
I was confused on what the different JXI commands do.
Now, there's no such thing as JXI. When I use the word JXI, X is a placeholder.
Yeah, variable. Yeah, like the different, like overall the different flags.
We only got 5 flags.
Okay, so there's
Carry, 0, sign, overflow, and less than. Yep.
No, never mind. I was gonna say something different.
Oh, okay.
Realized
Something about the cricket?
No. Something about
Because the cricket is definitely distracting the class right now. It's distracting me.
So Z is for 0.
Z is for 0, correct.
Isn't there a carry flag?
Sorry? No, go ahead. You raise your hand.
What do you use the carry flag?
Exactly. We should use the carry flag because the carry flag is also the borrow flag. So JCI, okay, so let me emphasize that we are using the unsigned interpretation here. Then we have to use JCI to else label. The fun part is right here, I don't need to compare anymore. Because even though, technically speaking in C, I have to compare A and B again, this time to check for equality. When you compare, it is updating all 5 flags at the same time. So the carry flag, the 0 flag, the sign flag, overflow, and less than flag, they're all updated at the same time when you perform the compare instruction. So that means if we only need to check the Z flag, we can just check it here. We don't need another compare instruction. Now, another compare instruction wouldn't hurt anything, except it just takes extra time that is not needed. Is that okay? So that is all done. Then we have this rather simple thing here, because A and C are both registers. CPR is going to work, copy register, and I intentionally preserve the ordering of left-hand side and right-hand side. So when you have 2 operands with any type of mnemonic, the left one is always the one getting updated. So that means it's easier to look at the C code and convert it into assembly code. So this one is now converted to CPR CB, and at the end label, okay, we just usually put a halt instruction so that the program will stop at this point, unless you have some additional code to perform. Then you have whatever code is supposed to be following this. So is that okay? Kinda?
We use the go-to and if label after the CPR.
Sorry?
We didn't use the go-to and if label.
The go to.
After the
Oh,
CPR.
okay. I forgot to implement that one. Okay, thank you. So a go to is just a JMPI, just like that. Thank you. All right. Cool. So is that okay? So to practice, basically what you want to do is to find very simple algorithms like finding the maximum of 3 variables instead of 2, and look at the C code, make sure the C code is working first, and then convert it into assembly code. Finding the maximum of 3 variables is actually not too bad because we have 4 registers. So you can assume that 3 of the registers contain the values that you need to work with, the inputs, and then the last register is going to store the maximum. Is that okay? Yep.
What if they were signed?
Hmm?
What if they were signed?
Well, that's a good question. So I'm going to bounce it back to you. What if it is signed? Because I'm expecting you guys to know the answer already.
You said there's a less than flag?
Yes.
How's that? It just knows if it's less than the other?
Okay, so this is telling me that you guys probably need to go back to review some of the earlier stuff. I think that was discussed in signed comparison somewhere. Oh, binary number comparison. So this is the module that you might want to kind of revisit because this particular module talks about the definition of the L flag versus the B flag and how they're different. And also it talks a little bit about when to use which flag. So you might want to revisit this particular module. If you find the way I write the module to be confusing, which is highly likely, then you tell me which section looks really confusing to you and what is confusing. In other words, with this particular sentence, I can interpret it like option A, option B, and option C. Which one is it? That is what confusing is there are multiple ways to interpret something. So if there's something like confusing here, I'll be more than happy to update it so that it's not confusing. But it is here already, so you gotta read it and understand it. Yep.
Is the left hand flag the same as the Y flag? Or
The what? The L flag, yes.
The line or
The what?
wasn't it labeled line flag?
Line?
Yeah, the line.
Lined?
Lying. Saying,
Oh, the line? No, the line flag is the overflow flag. So the overflow flag is kind of like a referee to the sign flag. So when the overflow flag is a 1, it's saying the sign flag is lying. When the overflow flag is a 0, it says the sign flag is correct. That's one way to look at the overflow. So are we good with this stuff so far? So a lot of these concepts, as you can see, is not independent to what we have already introduced in the past. In fact, I would say most of the concepts that we are using now is actually built upon the stuff that we have learned earlier in earlier weeks. So that means being able to clear away all the concepts that we have learned earlier is really important in this class. Is that okay or not? So, okay, so let's get back to giving you guys an opportunity to exercise and basically see if you can do conversion. How do you find the maximum when you have 3 variables? And you cannot use a loop because you cannot index through registers. So what do? You got 3 variables. There are several ways to do it. You can always say if A is less than B, then A cannot be the maximum. Otherwise, A is greater than or equal to B, B cannot be the maximum. So inside here, then you can say if since B is the larger one, then you have to compare B and C, right? So if B is less than C, then C is the largest of the 3. So your register D, which is going to be containing the maximum, is going to be C. And then the else is going to be the other one. So D is going to be B in this case. And then the else is really the opposite. A is greater than or equal to B, so you can rule out B to be the maximum. So you only have A and C to contend or to compete. So you can say if A is less than C, then the the maximum has got to be C, right? And then else, since A is greater than or equal to C and A is greater than or equal to B, A must be the maximum, so D equals A. Okay, I missed a semicolon here. There we go. So you can try to convert this into assembly code. That's one way to find the maximum. And then there are other ways too. So the other way to find the maximum is something like this. If A is greater than or equal to B and A is greater than or equal to C, basically you spell out when A is the maximum. Then you say D is A. Then you say else if, okay, if A is not the maximum, who is the maximum? Let's try B. If B is greater than or equal to A and B is greater than or equal to C. Now I think this one may not be needed, okay? But you know, it's still correct. And then the else, the catch-all else means it has got to be the third one. So C has to be the maximum. So there are quote unquote two ways to find the maximum when you have three variables. Yep.
Is it better to try and use less registers?
Huh?
Is it better to try and use less registers?
To use fewer registers?
Yeah, like do just 3 registers.
Well, you know, to not complicate things, you know, any further, I'm just keeping everything in registers. So this way you don't need to use memory locations and make your code unnecessarily long. Because the focus is, right here, the focus is the control structure, not so much how we access variables. So these two would make pretty good examples, you know, if you want to try out, okay, you know, I want to try out compiling code into assembly code, try these things out. Is that okay? Cool. Okay. All right. So this is something that you kind of have to do on your own. If you want more examples, you know, want more exercise, I can probably come up with more. But we can start with this. Did we talk about multiplication by adding repeatedly in this class? No? Okay. So if I want to compute, you know, C equals to A times B, but without using the there's no multiplication instruction, and I don't want to do the bit shift add, you know, version, which is kind of nasty in a way because we don't have enough registers. So that particular technique actually is a little bit complicated as well. So one way to do this, assuming A is unsigned and B is unsigned, then you can do it the pre-third grade method, which is basically adding a whole bunch of times, right? Okay, so this basically boils down to initializing C to 0, and then you say pick one of the two numbers, let's say A as a counter. So as long as A is non-zero, perform the loop. So in each iteration of the loop, you are just adding B to, oops, you're adding B to C, and then you're decrementing A, because A is now serving as a counter. So basically you're just adding B to C A many times. Now it's not the best way or the fastest way to do multiplication, but from the perspective of converting this into assembly code, this is another thing you can do. Yep.
It doesn't matter if you do prefix or postfix for that A, right?
Does not matter at all, because we are not using the value of the expression. We're only using the side effect of the decrement. Yep.
Is this how they do it, or do they do it a different way?
You mean real multiplication?
Yeah.
Yeah, this would be a pretty dumb way to do multiplication, because if you have, so let's say A is, so let's say this is a 16-bit processor, not even 32 or 64-bit, okay? If A is the largest possible unsigned number and B is just 1, how many times do you have to go through that loop? 65,536 times. Well, 35 times, sorry. So it's not very efficient, but from the perspective of just practicing, this is not bad, because this one has got a loop The other ones do not have a loop. So this gives you a chance to practice looping. So all of these are suggested exercises that you can do on your own. If you feel that I need more exercise, I need to have more practice, these are basically your practice. Any other questions? No questions? Yep, go ahead.
To multiply them,
Do multiplication?
how do they actually do it?
Okay, so there's hardware multiplication. So multiplication, okay, since you asked the question, and I think it's a legitimate question to ask. So let's say we have A, B, C, D as a 4-bit number, and you are trying to multiply that to E, F, G, H, okay? How do we multiply these numbers? Well, the usual way is you have A, B, C, D times H, right? A, B, C, D being a single number times H plus, and this one I have to be careful, A, B, C, D times G0. Is that okay? Because G is the second least significant digit, so that means we have to kind of line up things a little bit. Okay, so I'm going to line up things a little bit so that it looks better. Okay, and after this particular sum, then you're going to add some more, right? So whatever you have here, you're going to add A, B, C, D times F00, okay? And then you have another partial sum. Whatever partial sum you have here, you have to add it just one more time to A, B, C, D times E000. And then the final sum is going to be the product. Does this look familiar to you? It should, because it is the same way that you do base 10 multiplication. But remember, base 2 is easy. Base 2 is easy because H, G, F, E, E, F, G, H can only be zeros and ones. So either you have that term or you don't have that term. So that means it is a whole lot easier. You can actually do this using logic gates too. Is that okay? So does anyone want to actually see the code to do this using just registers? Or are you guys going like, who cares, multiplication? It's just multiplication. I think it's a good exercise. So let's go ahead and do it. Okay. So the question, or the most important part, is not the addition. Addition is easy, okay? Not a problem. Shifting this 0 in is not a problem because you can just add a register to itself. That it becomes a shift operation. The problem is the multiplication to whatever bit it has. Okay, how do we get to bit H, just H by itself? How do we get to bit G, just G by itself? How do we get to bit F and F by itself, and so on? That becomes the more difficult part. Okay. All right. So now that we understand what the challenge is, we'll just do a 4x4 multiplier, okay? Because otherwise it gets a little bit too long, so we'll just do it with 4x4 here. Okay, we'll assume that we want to compute A times B, okay? And we want to store the result in C. Is that okay? So I'm using register C as the actual output. Register A and register B are the two numbers that I want to perform the multiplication on. And register D is just a scratch register. I can use it for whatever I want. Okay. But before we do this in assembly, it might be helpful to look at this from the perspective of C and C++. So we want to do this in C and C++ first. Okay. So we know that one of these. Okay. So we'll designate which one is A and which one is B. So let's just call this A and we'll call this B. Register A and register B. So now the question is, how do I isolate H, bit H, so that I can determine whether I should add just A itself to C? How do I make that determination?
B mod 10.
Not mod 10.
Or mod 11.
You can do mod, but mod itself is the result of a division, and we're just barely trying to do multiplication. So let's not do division.
Is there some way to like bit mask it out so that it's the only thing left over?
Yep. So how do we single out a single bit?
Would you just like
You-
for it with
Not or.
Oh, it's and.
Yep, you can AND it. So we can say, okay, if B and 1, oops, B and 1, then we got something to do. So what we're going to do here is to say C plus equal to just A. And C obviously has to be initialized first to 0. Is that okay? In other words, what I'm doing here, this step here, is really just performing this step here. Because I'm singling out a single bit to say, okay, let's check, just bit 0 of B, which is bit H in this notation. And because H can either be a 0 or 1, if H is a 0, I got nothing to do. There's nothing I need to add to C. If H is 1, then I'm just adding A to C, register A to register C. Okay? So when this is all done, I need to do the bit shift. In other words, the next thing I need to do, which is related to G, there's a little shift operation here. So the shift operation can be done to A, B, C, D first, and then I multiplied it to G. In other words, if you look at this expression, the question is, do you think it is the same thing as A, B, C, D shifted once times G? And let me use extra parentheses to indicate what I mean by that. Would that be the same? Yeah, it should be the same, because this extra 0 is times 2. This is also times 2. And times 2 versus times G, because they're all multiplication, it is commutative. The ordering of those two multiplication should not matter. So that means instead of shifting G, I can shift A, B, C, D, which is in register A. I need to do a left shift. You look up all the instructions, we do not have a left shift operation. So what should we do? Add it to itself.
I was gonna say right shift, like,
Hmm?
could you right shift by 7 times 2? I mean, by 7.
Nope. Because right shift will pad zeros to on the more significant side,
Oh,
so
okay.
you'll end up losing the digits.
Okay, gotcha.
Now we do need a right shift operation on B so that we can single out that bit using the same bit mask. Yep.
I think I missed it. What's in C, right? Like at C plus equal A? What's the C in before that?
C is 0 to begin with. C basically is our product.
Oh, wait, I think I meant A.
In A is one of the numbers that we are multiplying. So A, B, C, D in the original notation is register A.
Okay.
I know it's confusing because in the notation A, B, C, D, A is representing a bit, but A, B, C, D as a bit pattern is register A. Okay, so moving on. So I have I have two choices here. In order to mask B with another bit, I can say if B and 2 this time, because 2 is 1, 0 in binary, it is masking bit 1 in this case. I can do it like this. But to do this in assembly, I would have to reload the register, another scratch register, which is D with 2, and then do the bitwise AND and stuff like that. Which is not too bad, I suppose. We can do it this way. And so in this case, we'll say, oh, okay, let's add A to C if bit 1 of B, register B is a 1, then we'll add A to C. But remember, at this point, A is already left shifted once. Which basically means this chunk of code here is really doing this part. We're paying attention to bit 1 and then doing the multiplication as well. And also adding that to the partial sum, which is register C. Is that okay? All right. So the next one is going to be if B and, oh, we got 1, we got 2, the next one must be 3. No, it's not 3, it's 4. So tech cannot count, right? 1, 2, and then 4. Why is it 4? No, it has to do with binary, but why is it 4?
The next power of 2.
Yep, exactly. We are incrementing the power. We're not incrementing the value itself. We're incrementing the power. So the next power of 2 is to the power of 2. And I also have to remember to left shift A by 1 bit. Okay. Every time you add A to itself, you're shifting to the left by 1. Is that one clear? Do we understand why A plus A is really A shifted to the left by 1? Yep. A plus A is also known as 2 times A, right? Which is also known as A times 2 to the power of 1, and that's why it is left shift by 1 in binary. Okay, so we keep doing this, and then we just have one more time, right? A plus equal to A again. If B and 8 this time, which is bit 3, just do the same thing. And we're done. So this is how we can do a 4 bit by 4 bit multiplier using very basic instructions. Because addition we have, okay? Bitwise AND we also have. And that's it. We only need addition and bitwise AND. There's no compare actually. Because when you perform a bitwise AND, the AND operation also updates the Z flag, which is what we are really checking here. So there's no compare, there's no need to compare to 0. Yep.
Is there a way to just left shift the B and then
Okay, so you can right shift the B, but you still need a way to isolate bit 0 if you're right shifting B. So you still need an AND operation to isolate one single bit. So there's no real quick and easy way to get out of this one.
wait, can we shift the other?
Whatever bit you shift out of B is lost. So that's why you can't really do much about it. Is that okay? Yep.
So it's like the reason you prefer this is that it's the same no matter what choice of operations for multiplication, whereas the other one, it just depends on how big of A.
Right, so the time complexity of this one is constant and it is short. So you can argue and say that, okay, what if A and B are both zeros? The other one wouldn't even go through one single iteration. But we have to look at the average case when we look at the complexity, and on the average, this one doesn't take that long. It is always the same. Almost always the same because it depends on the condition. All right, so now that we have the C code, do you guys want to convert it into assembly code, which is kind of the bottom line of what we're doing here? Okay, so I'll just copy and paste it here, and at this time we'll comment out every single line, which this particular editor is not very good at. So we'll go ahead and use the other trick. We'll save the file into the temp folder. We'll call it mode.ttpasm. And then I'm going to switch to my other editor, which can do all the fancy stuff. And we don't need the entire program either. We can basically just, oh, I got some extra stuff. Okay. There we go. There we go. This is why I like VI. You can do stuff like that. I actually had it not on this computer, but I made a syntax file for TTP-ASM, so it would actually highlight the mnemonics and also highlight the comments with a different color and stuff like that. But I didn't copy it to this computer. Maybe one of these days. Okay, so first of all, we have to initialize register C to 0. So the usual way we do it is LDIC with a 0, right? I mean, that's the obvious way. Load immediate C with a 0. Let's not do something that's boring. Let's do something that is less boring. Would that do the same thing? And which one do you think is faster? Yep. This one is faster because it doesn't need to access memory unnecessarily. This instruction, sub-cc, is only 1 byte. It doesn't have the second byte to store the constant that we're putting into the register. The only downside of sub-cc versus LDI is LDI does not change flags. All the flags remain the same when you execute the LDI instruction, but the subtraction instruction will update all 5 flags. So if you need to preserve the flags, do not use sub. On the other hand, in general, most of the time, we do not need to preserve the flags, then sub-cc is going to be faster if you just need to initialize a register to 0. All right. So the next one is to compare B and 1 to 0. Okay, so what we need to do, there's no easy way to do this without the LDI. So we're going to LDI D, which is our scratch register, with the bit mask, which is 1. And then we perform the bitwise AND, and we store the result back into D because we don't want to destroy register B. We want register B to remain the same. The AND operation would also affect the flags, especially the one that we need, which is the Z flag. So in this case, if it is 0, then we have a JZI and skip over the addition of A to C. So we're going to have a label here to indicate the next bit. Okay, so we'll call this bit 1. And then over here, we'll just say, JZI to bit 1. That's how we can do this. Do we have any questions back there? No? Okay.
I have a question.
Yep.
How do you know that you need to use JCI after the end?
Because implicitly, what this is saying is, okay, so implicitly there is a comparison to 0. Is that okay? So we are implicitly comparing to 0. But compare to 0 doesn't do a single thing, because remember, compare is nothing more than a subtraction. Subtracting 0 from something is that something itself. But we also know the AND operation is going to change the flags. So that means we can just rely on the AND instruction itself to change the flags and not have to do the actual compare. What about this one here? Well, that's pretty easy, right? Because we're just adding register A to register C. And then this one is just adding register A to register A. And then this one here is LDID 2 and D with B again. Then another JCI to bit 2. Bit 2 is right here, which is basically skipping over the then statement. And then the then statement is the same boring, add CA. And then we are adding register A to register A again. And then here, you know already, this is load D with 4, which is the bit mask. And then we perform the AND operation with B. And then JCI to bit 3. So skipping over here, we're going to bit 3. And this operation is just adding register A to register C. This is just adding register A to register A. This is LDI B8, D8, NDB, JCI to end, because we are pretty much done at this point. Another add instruction, and that's it. And it's going to be here, put a halt instruction. That should be it. Yep.
Scroll back to the start. I missed something that I wanted to write down.
Sure. Any questions? if you remove all the comment lines, this program is very boring. I mean, we're repeating the same thing over and over again. The only thing that's changing is what we put into register D. Is 1, 2, 4, 8. The rest of the program is just copy and paste and paste and paste and paste. Is that okay? Yep.
So instead of just loading like data into D, can we just add D to D?
No, the problem with that is when we perform the AND operation, it potentially destroys the bit of 1 in D, so we cannot rely on that.
Oh.
Yep. Now, obviously, you can say, if if the answer is if we go into the then statement, then D is preserved, because when you AND B with D and it is non-zero and there's only one bit of 1 in D, that means that one bit of 1 is actually preserved. So you can save that LDI and instead use an add instruction when you're in the then, but that means you also have an else that you actually have to load it with a constant. So that will actually complicate the program really unnecessarily, even though you are saving the LDI instruction sometimes and replace it with a shift. The saving is not worth it because you have to introduce additional jump instructions, and jump instructions are particularly nasty when it comes to affecting the efficiency of a processor. Does anyone understand why branch instructions, or especially conditional branch instructions, are really bad for modern processors? Can anyone imagine why that is the case?
Does it have to look up where to branch to?
No, not so much that. It has to do with modern processors make use of a technique called pipelining, which is not in the toy processor. So what pipelining does is, remember each instruction has potentially 4 cycles. You have fetch, decode, execute, and there's a quote-unquote store, where you store the result back into a register or store into RAM. So there are potentially 4 phases to the execution of each instruction. Pipelining is basically saying, what if I can just pipeline the whole thing? In other words, we have 4 actual pipes where they're staggered. So the first pipe would fetch, the second pipe would decode, the third pipe would execute, and the fourth pipe would store. So you can now, instead of using 4 clocks to execute one instruction, now you can execute one instruction per clock. Is that making any sense? So that technique is called pipelining. Pipelining works really, really well when instructions are just sequential. But when you have a branch instruction, especially conditional branch instruction, it doesn't like it. Why do you think it doesn't like it when you have a conditional branch instruction?
Because once you actually branch everything in the other parts of the pipe are invalid, you have to
You can invalidate a good portion of the pipe. So some modern architectures would actually follow both potential branches. So when you have a branch, it will actually have 2 sets of pipes to say that in case the branch happens, we go with this pipe. In case the branch did not happen, we go with this branch. So by the time the actual result of the branch is known, it would abort one of the 2 pipe bundles. Okay? But that's a lot of extra transistors, to gain that efficiency. But that's also why, if you are really looking for efficiency, you want to minimize the number of branches, because branching typically would break a pipeline, and then your execution of instructions would be less efficient. Just, stuff that, normally we don't have to think of, but when you're at this level, it becomes kind of important. The compiler is fully aware of pipelining as well, so the optimizer of a GCC compiler actually takes that into consideration. So it will give you the best combination of instructions to improve efficiency. It is to the point where an experienced programmer can look at the output of GCC and go like, what is that? Oh, that makes sense. Oh, this is so smart. Okay, so are we good with this code so far? Do you trust me? You're supposed to say no. Okay, so since you do not trust me, we're gonna have to test this, right? So we'll go back to, let me get rid of this one because I just updated the file. So mouse pad. So we'll test this program. Control A, Control C, and then we go to the assembler window, which may or may not be here. Yep, it is. Go to the source and go to line 1. Paste. Make sure it doesn't complain. Okay. The program itself is not really that long because we have a lot of lines that are just comments or open curly brace. They don't do a single thing. So when you look at the actual program, when you look at the locations, this program is 1C, so that's 16 plus 12, which is 28 bytes or so, 29 bytes altogether. Not too bad, 29 bytes. When was the last time you count your executable size by bytes instead of kilobytes or megabytes? So 29 bytes. But let's see whether it works or not, because this is why we're doing this. So we go to download as CSV, collect mode in the temp folder, and then we need the simulator, which I have here as well. Control R, reset the whole thing, go to the RAM module, load mode.csv, program is in, and we just have to inject some values into register A and register B that we are multiplying. What do you want to multiply? Remember, it can only be 4-bit wide, so we can have up to F, 0F in each one. So what do you want to multiply?
33.
33.
I didn't think of another number.
33 is more than 15, but we can make 33 the product, so we can have 3 and 11.
Sure.
Okay, so let's say we have a 3 here and 11 over here. B is 11 because A is 10. Okay, so, and then I'm just going to be safe. I will play it safe here and just go to logging. So with this program, if I'm not confident that the program does work, I'm going to log the program counter, and I will also log the registers too. Particularly register D, C, and B are important. So we'll register B, register C, and register D, and change every single one to base 16. Okay. And store everything in the file. So we want to select a new file, mode.tsv. I noticed that this may be my second time of running the simulator with log, so it may not work. We'll see. So now we can do a Control K. My ears. Control K. Looks like it worked. So we want to go back and look at register C because that is supposed to be 33 in decimal, which is what in hexadecimal? It's supposed to be
1F?
no. It's 2-1 because it's 2 times 16 plus 1. So 2-1 in hexadecimal represents 33 in base 10. And it is in fact 2-1. So I actually did not have to go through the log. Because I was expecting that I made some stupid mistake somewhere and it actually didn't work. Which is not uncommon. So are we doing okay so far with this code? Since somebody asked, asked about multiplication. What about using gate logic to do multiplication? Now that you know the trick, how do you use hardware? Okay, use individual adders and splitters and AND gates to perform multiplication. So think about that. Okay, instead of using opcodes to do it, if you want to implement a hardware multiplier, how would you do that? So that's kind of like a thought exercise. Okay, but you can use the same technique. It's just that the multiplication is easy because the AND operation is a multiplication. Cool. good one. But it came a little bit late. The moment we found 2-1 in register C, that would be perfect timing for that. Okay, so now that this part is done, I'm going to close this one. It's just that if you need a reminder of how binary subtraction works and what the flags actually mean after a subtraction, that would be a good module to revisit. So I'm going to consider this module basically done for now, unless there are specific questions. Are there any specific questions about this particular module? There's a lot of tedium in the conversion process, but when you look at each step of the conversion, it's not actually that bad. So the question is, can you do it step by step in a way that you don't lose track of the details? So if there are no questions about this for now, we're going to start a new topic. If you have specific questions, we can come back and deal with those questions. But if we don't have any specific questions, we're going to move on to the next really fun topic, because there's not a whole lot of tedium in this one. There's a lot of concept in this one. Calling and returning, dealing with subroutines. Okay, so let's open this one up. What time is it? We got 7 minutes. Okay. So with 7 minutes, we can at least get into the main concepts of calling and returning. Particularly, we want to talk about the concept of a stack. So section 3 talks about a quick digression to the concept of a stack. What is a stack? Since the prerequisite of this class is only 360, some of you may not have been exposed to the term stack that is specific to computer science. So what is a stack? In data structure, what does it mean when I say a particular data structure is a stack? What is the characteristic of a stack?
You can only put things on top and take things
from the top. Yep. But since that is the only way you can do it, so that means the ordering of putting things in and taking things out has to be it has to follow a particular pattern. So what is the term to describe that pattern? Last in, first out. Okay. Yeah, last in, first out. So last in, first out is the characteristic of a stack. Okay, when you put something into a stack, that last thing that you put in is the first thing that you take out of a stack. Now, that seems pretty abstract, right? So what I'm going to do is to unabstract it for you, make it really concrete. So think about you're helping a friend to move with a U-Haul truck, okay? So to make this even more visual, you can think about this U-Haul truck being extra long, but the cross-section area is kind of small, okay? So so you start to put things into the truck, okay? And the first thing, before you put anything into the truck, you're examining the truck, making sure the inside is clean and all that, right? And then you put down the map to the destination right at that point when you inspected the truck. And you forgot that you put the map in the truck when you're examining the deepest part of it. Then you start to load up the truck. Is that okay? You load up the truck, and then you close the tailgate. You just barely close the tailgate because we always have way too much stuff for moving purposes. And then you and your friend got into the cabin of the U-Haul truck, and then you're ready to drive. Then you suddenly realize, where are we supposed to go? Right? Where's that slip of paper? And then you suddenly realize, oh, when I was inspecting the inside of the truck, I put it down. So now the question is, how much work is involved to get that map back? What do you think? A lot of work. A lot of work. But why is that? Because the last thing that you put in is the first thing that you retrieve, right? So the first thing that you put into the truck, which turns out to be the map of the destination, is the last thing that you're going to retrieve. You have to empty out the entire truck to get to that one piece of paper that you accidentally put in and forgot to put it back in your pocket. That is the nature of a stack. Second example, you go to buffet. Okay, buffet places where you can take a clean plate from a stack. That's a stack. So that means the first clean plate that the kitchen or the people put onto the stack is going to be the last one to be used. Does that make any sense? So the ones that are on top are the ones that are going to be used, and then they will put it, back to the kitchen. They will clean it and put it back on top. So that means the tear and wear factor of those plates is not going to be very even, is it? The plates that are put onto the stack to begin with, they probably will still look pristine after 15 years, especially if the buffet place doesn't get very good business, right? But the plates that were on top, on the day one of the business, they would look pretty yucky in a few days, because those are the plates that kept being picked up, used, washed, put back onto the top of the stack, picked up again, and so on. Is that making any sense? Third example of a stack, your refrigerator, your fridge. Okay? So unless you're very disciplined and you check before you buy stuff and you go by expiration date of the stuff that you have in your fridge, most people, like myself, would just kind of forget about stuff that I already have in the fridge. Okay? So one day I go to the supermarket and go like, I really want to buy this. This looks really good. So I buy it, take it home, put it in the fridge. So do you think I would go through the trouble to get everything out of the fridge on a particular drawer, put the new thing that I bought all the way to the back, and then put everything back in, just so that I would use all the old stuff first before I get to the stuff that I just bought? No, I'm gonna put that new thing that I just buy, okay, apple juice or whatever, right there, okay, as convenient as possible, right? So what happened to that half-finished orange juice that I bought 3 months ago? It's still at the back of that, shelf, and probably is now becoming a mold garden with all kinds of colors. Okay, so that's another example of a stack. Okay, last in, first out. That apple juice is what I'm going to drink tomorrow, not that orange juice that has been in the back of the fridge for 2 months already. When do you think that orange juice is going to be discovered? When I move. When I move, then I will suddenly discover, ooh, look at that orange juice. It doesn't look so orange anymore. It looks like celery juice or grape juice. How can you turn orange juice into grape juice? Unintended fermentation.
That's a good invention to make a non-stack oriented fridge.
Okay, so to do that, there's one quick way to do it. So some of you, if you use my idea, you might become millionaires and billionaires, by now. Okay, if you make a fridge that has 2 doors, it's easy. If you just have to make it rotatable, so that you can put food in one direction, and then you get food from the other direction. So that's one way to do it. The second way is to turn it into a carousel. So each shelf is a carousel, and then you can just rotate it. So that way, you can even have an encoder to kind of encode when you put something into a particular sector of the carousel. So that way, your fridge can actually remind you and go like, hey, what about that thing? Has been sitting there for a while. So you can have a smart fridge that can do that. So you might find it a patentable idea. So if you have a few $1,000s to spare and get your patent, you might get rich because all those actual manufacturers may want to buy that patent from you. So are there any questions about refrigerators? Yes?
Just like, even though the first thing on the stack is released, doesn't the stack goes down, right? So the last thing that's put on the stack is like the bottom, and the first thing to go, right?
Okay, so the direction of the stack is confusing because in traditional term, the top of the stack is where you put things in, and that's also where you take things out.
Yeah.
So, but in the sense of assembly programming, we look at the stack kind of upside down. So the top or the high memory portion turns out to be the bottom of the stack, and then the low memory locations turn out to be top of the stack, and that's the portion that is active all the time.
And then the heap is like the exact opposite,
The heap is in a completely different memory
It's at the very
region.
bottom of the-
When you do allocation from the heap, we do allocation usually from the beginning. So from that perspective, you are correct. But typically in modern architectures or modern operating systems, the heap is an entirely different memory region, so it's not even contiguous to the stack. There's no way your stack can corrupt the heap or vice versa. But in terms of the direction of where you allocate, then the answer is yes. In the case of a stack, you allocate storage from top to bottom, high memory address to low memory address. But in the case of the heap, unless you have a lot of free operations, typically it's from low memory location to high memory location. Okay, so over the break, I want you guys to read ahead of me. This is the stuff that we want to talk about after the break, but we will have our practice exam first. So there are several things that we need to do after the break. And don't forget to clean up your fridge.